Year 13 revision, short revision video 3. So notice first of all in this question it requires that we show detailed reasoning, which means we must be very clear about each step of working that we do. Now, the first thing we need to do is determine the coordinates of the stationary points on the curve. So we're going to start by rewriting the equation of the curve. So we have y equals x minus 5 plus, and then in brackets, x minus 2 to the power of negative 1. Now, if we're looking for stationary points, we need to find dy by dx. So for part 1, we need to differentiate. Now, the first two parts of this differentiate very easily. X differentiates to 1, and minus 5 differentiates to 0. The next thing we have to do is differentiate this term here. Now, this is the format of a power. A function is being raised to a power of negative 1. So we simply multiply by the power, which is negative 1, reduce the power of the overall function by 1, so it becomes negative 2, and then we multiply by the derivative of the inner function, but the derivative of x minus 2 is just 1, so effectively we're multiplying by 1, which doesn't change the x minus 2 to the power of negative 2 at all. So we know at the stationary points dy by dx will equal 0, so we need to set this equal to 0, set our derivative equal to 0, and we then need to solve this. So rearranging this slightly, we can see that x minus 2 to the negative 2 equals 1, and then of course 1 over x minus 2 squared, if we rewrite that, is equal to 1, which means that x minus 2 all squared is equal to 1. Now, if we want, we can expand the brackets, simplify the quadratic, refactorise and solve, but it's actually a lot easier at this point here to simply say that either x minus 2 has got to equal positive 1 or x minus 2 has got to equal negative 1. Square rooting both sides and remembering the plus or minus root of the 1. So x is equal to 3 or x is equal to 1. Now, the question does ask for coordinates, which means we do actually have to go back and calculate our y-coordinates, substituting back into the original equation. This then gives us y equals negative 1 and y equals negative 5. So we have our coordinates of our stationary points. Now for part 2, we need to determine the nature of each stationary point. So we can see clearly from the diagram we have a maximum and a minimum point. So I'm just going to use the second derivative and differentiate again. So let's find d2y by dx squared. So looking at our derivative, which is over here, 1 differentiates to 0, and then the next part of this here is just a power function again. So multiply by the power, which is negative 2, which means we have 2 brackets x minus 2, reduce the power by 1, so it becomes negative 3, and then multiply by the derivative of the inner function, which again means multiplying by 1. So here's our second derivative, and what we need to do is evaluate that at each of the coordinates x equals 3 and x equals 1. So let's start with x equals 3. We can see that the second derivative, when you substitute in, will simply give us 2, which is positive. Therefore, x equals 3, we have a minimum point because the second derivative is positive. At x equals 1, the second derivative is going to take a value of negative 2, which is less than 0, so we have a maximum point at x equals 1, and you can see that corresponds with the maximum and minimum on the diagram. Now, part 3, determine the equation of the vertical asymptote. So there will be an asymptote, which is here, where there's a discontinuity in the function, and it's not defined for a particular x value. Now, when is that going to occur? Well, look at the original equation for the curve, and you can see there's a reciprocal part to it, and x equals 2 will cause us a problem because it will create a 0 in the denominator, and of course we don't have defined values here. So for part 3, the equation of the vertical asymptote, well, it will occur when x is equal to 2. Now, for part 5, determine the set of values of x for which the curve is concave upwards. A curve is concave upwards when the second derivative is positive. So we need to explore when is d2y by dx squared greater than 0. So that gives me 2 bracket x minus 2 to the power of negative 3 greater than 0. Divide both sides by 2, and I'm going to rewrite the left-hand side as well. So we have 1 over x minus 2 to the power of 3 must be greater than 0. And I'm just going to stop and think about this for a minute. And I'm going to think, well, when will the left-hand side be negative? When will the left-hand side end up being positive? Now, if x equals 2, we know we've got a problem because we get a 0 in the denominator. Now, if x is greater than 2, then this portion here will be positive. Cube it, you'll still get a positive result, so we're greater than 0. Now, if x is negative, we'll end up with a negative value in the brackets. That then will become cubed to still be a negative value, so that won't work. So the curve is concave upwards when x is greater than 2. So that means we have a curve that's concave upwards after this asymptote here. So this portion of the curve is the portion of the curve which is concave upwards.